Welcome, friends, to another episode of For Your Reference. This is the web series where myself and my friend Noah, we take a look at the
Hello.
Rust programming language. And, this web series is aimed at beginners. This is episode 3. In this episode, we're going to take a look at ownership and memory management and how Rust deals with this kind of thing, and how this can be somewhat different than any other programming language you may have worked with in the past. So anyway, Noah, it's nice to see you. Good for you to join.
Hey,
how are you?
how's it going, man?
Yeah. So this is an exciting episode.
I'm looking forward to it. It seems like, just reading about it, it's like one of the more unique features of Rust, and I think it's going to be illuminating for a lot of people.
Yeah.
You know, it was for me when it's like kind of clicked for me.
Yeah.
So
Cool. And so let's just take a step back before we sort of talk about this thing. So we're going to be talking about ownership and really how Rust does memory management. And of course, Rust is focused on safety. So there's a couple contracts that Rust makes with us as we write our programs, and we'll talk about those rules and how Rust utilizes those rules. But let's just take a step back before we do that and talk about programming languages in general. And, so when you're talking about computers, especially, in particularly electrical computers, right, they have some memory. And some people say that memory is all a lie or whatever, and the operating system just makes it up. But essentially, every program has some data, right? And how that data comes into existence and disappears later, so that the computer can reuse the memory that was associated with that value later. Every programming language has to deal with this, right? To get any sort of real work done, you're going to have to do this stuff. Typically, especially in the last 20-ish years or so, lots of programming languages use garbage collectors. There's lots of different kinds of garbage collectors. They all kind of have their own trade-offs here and there. Some of them, like for instance in Go, focus on latencies and pause times. Others, like the ones in Haskell, focus on throughput. Or maybe, maybe there's other kinds of trade-offs you can make, like complexity of the allocator. So for instance, in JavaScript, we have generational garbage collectors, which, can be very crazy in how they work. And then, of course, there's also lots of knobs that programmers can turn with these garbage collectors to tune them to their, preferred use case or whatever. And then, of course, there's also reference counting, which is sort of like I don't want to say the weird stepchild, because it's in some sense the simplest one, where you basically are just counting things, how often things are referenced, and then deallocating when you reach some counter of 0. Of course, Swift uses a reference counting garbage collection algorithm, but Rust by default, at least, is sort of the 95% case, does not use a garbage collection algorithm at all. The garbage collection is done at compile time, so to speak. You can opt into some kinds of reference counting if you so choose, but in general, we're not going to talk about that in this episode, and it's not really a thing that you're going to use for sort of the 95% case, if you will. So anything to add there, Noah, about garbage collection or whatever?
you covered most of it. Yeah, I mean, my main experience with it is I did a lot of Java and a bit of a fair amount of Swift as well. But I mean, this sounds a bit different to me, and sounds like it's optimized for performance, it sounds like.
Yeah,
so.
Right. And that's an important point, is that Rust is, of course, aimed at some environments or some kinds of programs where garbage collection is just simply not acceptable for a number of reasons. Maybe it's performance reasons. Maybe it's for just the environment in which your code runs. You just can't do it. How do you garbage collect an operating system, for instance? I'm not sure. By default, at least, Rust aims for a model closer to C or C++, where you're doing manual memory management. This becomes, the job of the programmer, so to speak. In those programming languages like C and C++, you're going to call malloc and free, right? So in Rust, you don't really have a malloc function. There is like maybe in some memory module or something close to malloc. But for the most part, by default, for your 99% case, you're not going to call any kind of malloc. And the free equivalent is a function called drop. I'm actually using it here in this program, but you actually don't necessarily even call that as well. Rust sort of does this for you, and we'll get into that as we delve into this. And this is going to be very similar for our viewers, and I know, Noah, you're very familiar with this, is automatic reference counting, kind of inserting these decrement calls at the right place. And so let's just before we get into that exactly, we're just going to take a look at this very basic program. I've got a data type called an accumulator. I make one of those accumulators here. I'm like allocating, right? Even though I don't call malloc, I'm just like creating the value, initializing this memory space, right? Here's an example of creating a vector. So vector is a little bit unique in the sense that vector has some heap allocated memory associated with it. So by default, everything in Rust goes on the stack, but there's also another place in memory that's called the heap. You can look in the Rust docs exactly what the difference between these two things are. Low-level programmers who are watching this video probably are very familiar with the stack and the heap, but generally speaking, you could just think of it as, is it a local variable inside of a function, or is it like something that has to grow dynamically in size, right? And also there's some other kinds of values that you can make that may have other kinds of resources associated with them other than memory. For instance, here I'm opening a file, and there's some kind of like file descriptor, or maybe like operating system stuff associated with this. And so the question becomes, for any programming language, when is it safe to like deallocate, destructure, maybe close this file, deallocate this heap memory, sort of invalidate accumulator? When is it safe to do that? And in particular, we want to make sure we do that exactly once, right? We don't want to do it not at all, because we, might run out of memory, or for instance, never close our files. And we don't want to do it too many times, because as the, C and C++ programmers watching this video might be aware, double free is like, also a bug. Yeah. So let's just take a look here at this program and just build some basic. Wait, this is the wrong program. This is the wrong program. We want to look at part 1 here.
What was that one?
That was part 2. We went too fast.
Whoops.
Right. So this is part. So this is just a basic program, right? So it has a main function, and we have a binding. Or you could call this a variable. I like the name binding, and we'll see exactly why I like the name binding, especially in Rust, as we get further into this episode. But so we have a binding called literal, and here's the value. And it doesn't matter too much what the value is exactly, but we have it, right? And so we know that just from like other programming languages, like this kind of line right here is illegal, right? And actually the Rust, the compiler, my editor here, is complaining about this and says, oh, we've tried to use literal before it became like valid, right? Before it came to life, right? And then of course we're allowed to use literal anywhere within this function all the way up until our closing curly, and like that's sort of the lifetime of this. This is how scopes work, and like 99% of the programming languages is pretty straightforward stuff, right? Rust has the ability to create scopes for many different reasons. Of course, functions. They also create scopes when you make if statements. But you can also just create like naked scopes, if you will, like scope literals, or maybe I think they're called blocks. And this is just, inside this main function, I have this sort of value in here called another lit. And another lit is only valid within here, right? It's not valid until this line, and it's no longer valid after this line. So if we go like let x equals another lit, this will also be a compiler error. As you can see, it's complaining, right? And here's just another demonstration of the same exact concept here, except I've used an if instead of like a naked block, right? Again, we can't use this if literal, which was created inside this thing, because it has gone out of scope, right? Does that make sense, Noah? Any questions, concerns, feelings here?
This feels pretty standard. I think the only thing that some people might be a little bit like unusual is I think is a little unusual is the like kind of naked block there, but even that seems pretty straightforward. It looks like it's just executing whatever code you put in there, but it's in kind of its own.
Right. And like it's definitely like a newer thing. Like I think more recent versions of JavaScript have blocks. It actually turns out that like some people just use them for kind of namespacing, right? Like it's just like, oh, I want like this kind of isolated space, right, to do my computation or whatever. But in Rust, they turn out to be even more useful, as we will see, because of how scopes play into memory management.
Okay.
All right. Let's move on. So we've already looked at this program briefly, but we'll keep looking at it. So, so we did briefly talk in last episode. We talked about structs and enums and how to create data and stuff like this. So I've just created this struct. I've sort of allocated that value on the stack here. We talked about how vectors are another kind of value, but they have an additional resource associated with them. They have this like dynamically growable and shrinkable segment of data. That's this, in this case, is 1, 2, 3, but we can add more things if we wanted or remove things if we wanted. And we also have a file which has like an associated resource. So the question becomes like, when is it safe for us, either as manually or for the Rust compiler to automatically sort of insert the free call, insert the drop call for us? And so actually, if we just think about our intuition from the previous program, well, like actually, why don't we just like put them at the end of the function? And why we put them at the end of the function is because, well, the binding that was sort of holding on to that value went out of scope. And so if we call that binding a owner, and then we give that owner some rules, we can sort of extrapolate this rule and just make this a general contract that all programs in Rust will follow. So here are the rules for ownership, and we'll sort of delve into each one of them as we go. But so every value in Rust has an owner. That's always true. There can only be one owner at a time. And when an owner goes out of scope, the value is dropped. And, sorry, you were going to say something?
No, I was going to make a Highlander reference, but that's fine. There can only be one. No, nobody. I'm myself. Go ahead.
So here in this program, just to sort of drive this point home, accum is the owner of this accumulator. Dynamic array is the owner of this vector. Open file is the owner of this file. And so here at the end of the function, Rust is going to sort of automatically insert, like transparently to us, it's going to call this drop function on accum, on dynamic array. And we have done this manually here. We've decided to manually drop this file. Maybe we want to drop it early because files are particularly interesting, right? Because like maybe you want to get in there and get out. Only one program can hold this file open at a time. So maybe you want to do it a little early. But so even if we decided, oh, okay, we're not going to manually do this, Rust will sort of automatically put it in at the end of this function, right at this closing scope, right? So owners are associated with a scope, and when that scope ends, that's when Rust decides it's now safe to exactly once free that resource.
And so like the drop for like open file.
Yes.
That one knows like to do something special with that. I don't know. Or does it have to do anything special, or maybe it just a free?
Excellent question. So I think what you're referring to is, well, yes, we have this additional resource, which is like close the file, make a system call to like, file close or whatever. Where do we write that code? So Rust has a trait called drop, which is essentially for any kind of value, you can write like a special destructor function. And that's really the function.
Call into there when drop's called.
Correct. That's really the function that is run to destructure. And so in C++, I think this is called resource allocation is initialization or whatever. And essentially what that means is, when the file value is destructured, also the file that was associated with is closed, everything's cleaned up. Here in the vector case, the vector goes out of scope and the heap allocated like segment of memory is freed. Okay, cool. Thus far it seems pretty straightforward, right? Nothing too crazy.
Yeah, this is pretty easy.
Okay, all right. So let's so this actually has pretty strong implications, even though the rules are relatively straightforward. So let's take a look at the third part here. All right. Oops. Main. So I said that one of the rules is that you can only have one owner at a time. Well, that's true, but you're allowed to change owners. So here's we just kind of have this program built into 4 little parts here, and so I've given myself some tight scopes so that I can demonstrate certain things. But here's a vector, and then we print that vector, and then we do an assignment here, right? We say, oh, I have this new binding called vec2, and I'm going to assign vec1 to it. And if you've used other programming languages, this probably seems like a no-brainer. We know exactly what this program does, but in Rust, this actually means something slightly different. So this line right here is actually called a move. And why is it a move? It's a move because vec1 was the owner of vec, right? And then right here, we gave that ownership to vec2. And so that's why this program right here, which is exactly the same, I'm just going to recomment this line. This program right here actually is a compiler error. Because these lines right here are exactly the same, but what I've done here is I've tried to print vec1 after I gave away that ownership. So I was able to print vec1 here, but I was not able to print vec1 here because I've moved that ownership over into vec2. And so there's an additional wrinkle here, which is that you can move ownership by doing an assignment, but once you do that move, the previous owner essentially becomes invalidated. There's this notion of invalidation, and the Rust compiler tracks which bindings are valid. And at this point, it says the vec1 no longer valid. At this line, that becomes true. So to make this actually compile, you'd have to do this. And people are like, what's going on here? We'll talk about that. And why? So this all has to do with the fact that Rust wants to make sure that all memory is safe to use, when it's safe to use, when it's safe to free, exactly once, right? That kind of thing. Let's just briefly talk about another wrinkle, which is called copying. So here I have a num, and it's 3, and then I do this assignment. And if you believe me about these 2 previous programs, you're like, oh, this is moving ownership, right? Previously num1 moved it into num2, and actually you would expect this line to be a compiler error, but it's not. Turns out that really simple.
Num1, you mean, right? Would num1 be the line before?
Yes, you're right. I apologize. Num1 would be the compiler error. Yeah, you're totally right. You would expect this line to be a compiler error, but it's not. And the reason it's not is because all the simple types, like numbers, floats, booleans, tuples of these small types are marked in a special way such that the Rust compiler recognizes them as copy types. And so right here, we're actually taking the number 3, the value 3, and we're copying it into num2. And so actually, there are 2 separate owners of 2 separate values. Num2 owns its own version of 3, and num1 owns its own version of 1. And so that's why this is still okay.
So it's still following that rule of one owner.
Right. It's just actually literally 2 different values.
And if we go back to that one that was an error.
Yes, this one up here.
Does it say something doesn't it say something about that? Or
excellent question. So let's actually compile this thing. So if I say cargo run bin, this is 2, right? We're on 2.
Yeah.
Okay. Oh, I
forget. Did you say?
We're
I
on
forgot
3.
if you said something about how this was set up. You have 3 different. You have a bunch of projects here, right?
Excellent question. So let me clear this out. Remove our target. Okay, so if I say LL tree here, so I'm using a feature of Cargo called workspaces. So essentially, what I can do is I can tell Cargo that I have some sub projects, if you will. And so this is useful if you want to set up a large, mono repo, so to speak, with many crates. Maybe you have a few libraries that you want to publish separately. You can use this workspace. So I have built a workspace for each kind of segment of our episode. You can learn exactly how this works in the Rust book or in the Rust docs or whatever. But that's why when I run, I'm also giving this additional. I'm telling it which one I want to run.
Oh, cool.
So,
all right, so we're running that, and then we get oops, and then...
Right. And so actually, this leads into what we were just talking about a moment ago. It says, well, here's your vec1. You did the move here, and then you tried to use the value after you moved it. And that value does not implement the copy trait.
I like how they add that kind of...
Yeah.
which did not.
Yeah, I'm I've been using Rust for a while now, and I got to be honest with you, the Rust compilers, errors generally speaking are excellent. They
Yeah.
have like, they have
Yeah.
this like nice like, yeah, of course, all the colors, and then they like tell you which lines are doing what, and sometimes there's even like, not in this particular case, but sometimes there's even like a tip, and it'll like either give you a link to like some Rust docs or like tell you exactly what it thinks you should do to fix the problem.
Yeah, this is one of the I've heard is one of the goals for Swift compiler to get to this level.
It's pretty good. It's pretty good. They really focus on trying to make it like, I think they realize that their programming language has sort of a Rust tax associated, and they're like, well, we'll like give you all this other stuff.
We gotta make this,
yeah. So anyway, yeah. So helpful messages are helpful. Okay, so as we were saying, you can move values, but by default, they are move unless, of course, the value of the type is a copy, or the type of the value is a copy, and in which case it actually does a copy.
Cool.
You can also, of course, annotate your own types with copy. That you can look in the Rust documentation of how exactly to do this. Copying, of course, has potentially performance implications associated with it, which is why it's sort of opt-in, right? These simple types are considered insignificant performance to do the copy, right? Okay, and then one final thing is like, okay, well, is it possible to do a copy with move types? And the answer is yes. If the type implements a special trait called clone, that means it has a clone method. And right here, instead of doing a move from vec1 into vec2, what we're doing is we're taking vec1, cloning it, deep copying it, so to speak. And now there are two owners of two separate values, just like here, except there's this like indicator that this is happening. It's the call to the clone method, right? And so I've made this thing mutable. And so if we run this program, let's go ahead and do that. We actually see that when we print it the first time, it's 1, 2, 3. When we push a 4 into this and then do that, we actually have two separate pieces of memory, two separate values, two separate owners of those things. So here, right here, it's actually dropping both vec1 and vec2.
When you made it mutable just so you could do the push,
so I could do the push, so I could demonstrate that it's really two separate parts of memory, right?
If it wasn't mutable, you couldn't do that.
Correct.
Is that right?
That's correct.
Okay.
Let's double check that. So let's see
like
some nice compiler errors. It says can't borrow is mutable. Consider making this mutt. All right.
Cannot borrow. Interesting. Okay.
Yeah, we will talk about borrowing and referencing a little bit at the end of this episode, sort of to tee up the next episode.
Yeah. Sounds good.
All right. So feeling good? Not too bad, right?
Yeah. I think it's like you think you basically showed us you can move the ownership, or you can copy it, or you can clone.
Right.
And I guess clone, you said, is another trait potentially, right?
Correct.
Okay.
Yep.
Cool.
We didn't talk in depth about traits anywhere in this series, but we have definitely referenced them many times. They're basically pieces of like common functionality that many types can implement, right?
Okay.
Yeah. And it's like, oh, suddenly by being clone, I have this nice clone method, right? Okay, let's go forward into 4 here. Source, main. All right. All right, so this is a little bit more complex of a program, maybe a little bit more realistic. So in the first episode, we worked on a program that, calculated the sum of some files, right? And so here's a similar struct, but I have done something different. Instead of the struct having the sum itself, I've put a vector of numbers in there, so that when we do we're sort of keeping track of all the numbers we're going to sum at a later time. And
that's the same type that comes out of that. That was like a macro right before. So that's the
correct.
The vec. Okay.
Correct. So just as a sort of side note, but important thing is, well, what happens with fields? Like, who's the owner of these items? Because there's no necessarily binding associated with. There's no let, right? Well, it turns out that this struct is the owner. So when you have a maybe let accum, as we do here. This is the owner of this whole accumulator. So when this thing is dropped, the items are also dropped. Does that make sense?
Yep. It just basically releases all the fields, and then
right. And this will happen sort of indefinitely recursively. Yeah, exactly. Okay,
Okay.
so let's take a look at how this program works. So here we're allocating up a vector, and then we're going to say, I want to know what the sum of that thing is, right? So we're going to call this function called takes ownership sum, pass in that thing, and get a thing, and then print it out. And so let's just take a look at this implementation. It's pretty straightforward,
Weird name
right?
for function.
Right, exactly. So here, this is pretty straightforward, right? It takes this vec accumulator as the argument, passes back a thing, starts a sum, accumulates all the items up, and then returns that sum.
Gotcha.
Well, the question is, who's the owner at any given time? I told you there's only one owner at a time. What's going on here? Well, by default, when you pass an argument to a function, that binding, this parameter binding, instead of a let binding, this parameter binding, that becomes the owner. So here, accum1 was the owner, and then just like, and I'm actually going to pull this up, just like in our third program, there's an analogy to be made here.
It's like a move.
Yeah, exactly. There's an analogy between this and this. So what we have done is here we've done an assignment that did a move. Here we've done a function call that did a move. So now accum has moved its ownership into owned accum. And so here with this comment, I've said, oh, owned accum goes out of scope. We are no longer the owner. So Rust drops it. And you can imagine there's a drop call here, right? Does that make sense?
Yeah.
This and this are basically the same thing in some.
I mean, it's very, it's surprising, definitely, but.
Right.
That makes sense. So basically, now this
So-
variable that I've allocated in main, I passed it in, and now it's like owned by this function.
Right. And exactly your
you know,
point.
now
If I
it's
try
dropped.
to if I try to call the function again, because I'm like, oh, maybe I've done some processing here, like adding new numbers to some. If I try to calculate the sum again by doing this, the Rust compiler is going to complain. And let's actually run the compiler here. Oops. Cargo run bin. This is 4. It says, okay, there's a couple things. That's annoying, but it says, a move occurs because accum has type available, right? And it passed it into this thing. Value was moved into the function, but then we tried to use it again on line 36. And so this is exactly the same error as over here, right? We can't write this line as well as we can't write this line because we've tried to use a value that has been invalidated, right? This owner has been invalidated in the same way that vec1 was invalidated over here. So again, we can't do this. So we got to comment this out.
Wow.
So all right, this is stupid, right? Okay, how am I supposed to make a thing and keep using it after I pass it to a function? I want to be able to call functions on it. So you could exactly. You could do something like this where, okay, well, I'm going to pass it in. This owned accum becomes the owner, but I'm going to pass it back. Here's a tuple of 2 values. One is the accumulator that I got, and the other one is this. And here, Rust won't call drop on the accum because it's going to pass it back. Right? And so you could do something like this where, printing all this stuff, and then we give and take. So we give it here, we move accum in, and then we take it back and assign it to accum3. So now accum3 is the ultimate owner of this value. And so, of course, accum3 is in the scope of main. So somewhere down here, it's going to be dropped, right? Does that make sense?
A lot of work, but
yeah. So I think if Rust stopped here and was like, we've solved the problem of memory management and double freeze and all this stuff. We've given you these ownership rules. We've given you the concept of ownership. If they stopped here, I think no one would use the programming language, right? Because this kind of thing is super annoying. So I'm just going to kind of tee off the next episode, which is there is a way in Rust to sort of loan out something without giving ownership. So such that, for instance, in this case, I would really like to continue to own accum1 within main. Accum1 would like to remain the owner of this value, but I want to sort of loan it out to this function, sort of temporarily, right? And again, we won't talk too deeply about references. That this feature is called references, or aliasing is more generally, right? Usually it's like a pointer type in other programming languages. So Rust has a special pointer called a reference, in which case Rust allows you to do this this loaning of ownerships, or you don't really loan the ownership, you just loan the value without memory safety issues, because of course pointers have all kinds of problems associated with them. Humans are not good at bookkeeping, so there are rules with references as well. All right, feeling good thus far, Noah?
Yeah, I mean, it sounds like I think it's just a surprising thing, but I think it sounds like you're saying there's a good way to get around it that we'll talk about eventually.
Exactly.
But,
And just to drive home this point as well, this is still a compiler error here, because Accum2 was the owner, and then we moved that ownership into this thing, and then we moved it out, and we're not allowed to use Accum2, even though Accum3 is pointing at the same memory, so to speak.
What is it called? What did you say it was when you get rid of the
invalidated?
Invalidated. Okay.
Yeah. So this line is an oops. This line is not, even though it's actually the same memory. It's just how the Rust compiler works. Cool. Okay, and again, there's another analogy to be written between this program and down here. Here's a special function. It's really boring, but instead of this like accumulator thing, I have used one of these simple types that implements copy. So actually, even though I quote unquote moved, but I didn't move 5 into this function, I am still able to use inter. Inter has not been invalidated because it was actually copied, right? Remember, it becomes its own owner of the value. This value 5 here is still like safe to use. It was copied into the function, so to speak.
So some other int was dropped, and so you still have access.
Correct. It's exactly right.
Cool.
All right. I think that's pretty much it. I think, this is a very hyper-focused episode. I do want to end with kind of a little bonus section here about the drop function. Again, normally you don't write it too often manually by yourself, but in cases where you do, maybe like for instance, so with files or something like this, you want to close them as early as possible. This is we've kind of learned all the rules to understand exactly how drop works, because I think before the show started, Noah, you actually asked me like, well, what happens if I like try to call drop twice? And actually, this is a compiler error, and we actually know we will be able to tell exactly why this is a compiler error,
just learned, right?
Just because of what we learned. So I'm just gonna pull up my browser here, and I'm gonna go to Rust mem module drop. So here's like the standard memory. Okay, that's not what I want. Here we go, this guy. And we'll just take a look at the source code. So this is what's in the standard library. So here is the implementation of the drop function. This is always like a really fun moment for me to show new programmers of Rust what the drop function does. It does exactly nothing. It's an empty scope. And okay, so why is this a compiler error? Well, drop is a function, and if we take a look at the implementation, the type of it takes a generic T. This is a generic, so any type, anything, you can pass anything you want to drop, and this is an owned T, right? In the same way that this is an owned version of vec accumulator, this takes ownership. This function takes ownership of that accumulator. Here, drop takes ownership of whatever value you pass to it. And so that means, as you know, suddenly A has become invalidated, right? And so that's why we can't use it again. It's not just that I can't call drop twice. I can't call anything on it, right? So for instance, if I try to print it, like whatever, this will actually complain. For exactly the same reason. We have used an invalidated value.
But I could call, I just thought of this, like I could call drop on the I64 values, right? As much as I want. It'll just make copies.
Let's see what happens, actually. I'm not sure. There you go.
They don't care.
Your answer.
Okay. So that does nothing, right? Or I guess it drops a copy, right?
Yeah. This is like a total waste of time, right? Because you like copy in a 5, and then you drop that 5, but you still have your own 5.
I see. It's really interesting.
Okay. Yeah. Fantastic. I think that's pretty much it. Anything else you want to add before we end this episode?
No, I mean just that drop implementation is just
Yeah, it's kind of funny because it's like it doesn't do anything. So you can imagine. So this is just a scope, right? So Rust is going to insert its special drop call at the end of this scope because underscore x goes out of scope. As we discussed, I think earlier in this episode, if the type associated with X here has a drop implementation, that will be called as well. So like, maybe some heap allocated memory will be removed, or, a file will be closed, or a socket will be closed, or whatever.
If it inserts drop, isn't it? It doesn't call it. It's a call to some other drop. Is that what you're saying?
Correct.
Okay.
You can philosophically think of the compiler as inserting drop in the places where things go out of scope, but it's not.
Sure?
It's not necessarily literally this drop.
Oh, okay. It could be.
It could be. Most of the time, it's actually probably nothing, because a lot of values are allocated on the stack, and stack frames are automatically just cleaned up. There's nothing to really do.
Gotcha.
But again, when you have resources associated with your values, like heap allocated things or files, whatever, those things actually do need to be cleaned up, right?
Makes sense.
All right. I think that's pretty much it. Well, thank you for watching. We'll see you in the next one.
Bye.